Hello, we are Team 7, and our topic is Proximal Policy Optimization Algorithm. My name is Jungmin Park, and I'll start the presentation. To understand the proximal policy optimization, we need to know about reinforcement learning. We have an agent making an action under some environment. The action of agent affects the environment and the state changes. By the change of the state, we measure how good the action is, and agent evolves through the feedback of the reward. The action of agent is determined by deep neural network, and the feedback is given by the gradient descent. Therefore, there is a choice of implementation on the loss function. Policy gradient method uses very natural loss function, which is average advantage over each simulation of environment and agent. However, policy gradient method has a poor performance due to the problem that large policy update may destroy the whole learning process. So we have a TRPO algorithm, which uses Ka divergence term as a regularizer to prevent large policy change. However, the beta value here is really hard to tune properly. To resolve those problems of policy gradient and TRPO algorithm, proximal policy optimization paper suggests two proximal policy optimization algorithms, which are clip surrogate objective and adaptive KL penalty coefficient. Clip surrogate objective uses clipping to implicitly encourage this RT value to be close to 1. This RT value is 1 when old and new policy are the same. So the clipping leads to the small change of the policy, which is exactly what we want. Adaptive KL penalty coefficient resolves the problem of TRPO that finding the proper beta value is difficult. Adaptive KL penalty coefficient changes beta value adaptively through the training process so that we can make the KL value to be close to the target KL value. Here are the detailed updates of the beta according to the KL value in the training. This paper was published in 2017, so many follow-up studies have been conducted. We found 3 variants of PPO. The first paper, POP3D, suggests the lower bound to the total variance of divergence. The second paper, TRG-PPO, tweaked the clipping to be triggered on a trust region. The last one, TPPO, improved the previous paper by modifying the clipping to be able to roll back if necessary. We tried to improve the PPO algorithm by combining those two PPO methods, clip surrogate objective and adaptive KL coefficient. We first thought of combining two loss functions from each method and finding proper gamma value. However, by simple calculation, we confirmed that this new loss function reduces to this form, which is simply a combination of clip surrogate objective and KL penalty term with U epsilon and beta values. Therefore, mixing two PPO methods by linear combination of each loss function is equivalent to adding KL penalty term to the clip surrogate objective, which seems to be not done before in the literature. Therefore, we tried to implement this improvement approach.
Hi, I'm Sanguk, and I will continue to explain how we implement our algorithm. First, we use stable baseline 3, a PyTorch implementation of PPO. Since it contains only clipped surrogate objective, we implemented previous adaptive KL on the baseline. For evaluation, we use Pong as training model because robotics simulation requires high computing powers. Our algorithm used the original setting for decaying beta, but its initial value is changed. We tested with various values for two parameters, target KL and beta. Additionally, we compared the algorithm with the original ones, fixed KL and clipped surrogate. Any other parameters, like learning rate, epochs, are same as paper. The training was successful. Our algorithm with one of the best parameters results this video. So in this video, the parameters are 0.1 for target KL and 0.1 for beta. Now I will talk about evaluation and observations. First of all, our modification results better accuracy than the original. And we find that three characteristics by the value of parameters. I will explain this in the following slides. First, our algorithm outperforms the original paper under the best parameters. In our experiment, 0.1 for target KL makes smaller loss than the PPO as in the graph. We tested with 4 different values for beta from 0.1 to 100. The improvement was, as you can see, was almost same among the best beta values. We found that the previous observation also works for the different target KL value. We trained the model with different target KL value 0.03. The initial value of beta does not affect on accuracy, as you can see. The initial value of beta does not affect on accuracy, as in the previous experiment. And next, we found that the fixed KL penalty does not help growing accuracy. We fixed beta value during the training to mimic fixed KL penalty in the paper. With the fixed beta value, we expected the gradient of loss function will be dominated by the penalty term. As expected, the backward propagation caused the KL to converge to 0 and the loss function didn't decrease. Finally, we found that large target KL value causes the regression of accuracy. Since the target KL value is bigger than the real value, beta always decays in the iterations. The value does not recover from 0 when the target KL is 0.03, so the KL penalty term becomes meaningless. As the result, its loss function converges to the same value of one of the clipped surrogate objective. To sum up, we studied how we can enhance the PPO algorithm. We proposed the linear combination of the loss functions, clipped surrogate objective, and adaptive KL coefficient. We first mathematically verified that mixing two functions are equivalent to the adding KL term to the clipped surrogate. We then inspect that our approach outperforms the original algorithm. Also, we claim that two observations on the hyperparameters. One is that our method does not require fine-tuning on the initial beta value, unlike fixed KL penalty. The other is target KL value should be sufficiently small or it converges to clipped surrogate. This is the end of presentation. Thanks for listening.